So now this is just some theoretical aspects of all this. Let us get back to put string, main, etc. Now, okay. So recall that I said put string is of type string arrow IO unit. Put string takes a string as argument and returns the unit value of type unit, but it also produces a side effect when the value is extracted. Okay. So even though we don't use the string values, its value is implicitly extracted, and that's why the side effect is produced. Okay. So the side effect is that of printing the string on screen. Okay, this is the side effect. You can have lots of other side effects. Okay, so now main is of type IO unit. Main is always of type IOA for some A, whatever the A may be. Right. So we have these things so far. Now put string prints the whole string on screen. Put string line will add a new line also. Yeah, will print so put string line is actually equivalent to put string plus plus new line. Notice that I am putting this whole thing inside parenthesis. Right, I am treating string plus plus new line as a single argument to put string, and whenever you provide a complex expression as an argument to a function, you have to enclose the complex expression inside parenthesis. Right, I hope you recall the rule. Whenever so you would write I don't know, sum of L, where L is a list, but you would write sum of so you would write even sum of 2, 3, 5, but you would have to do this. Right, so this is the point. Okay, I mentioned chaining actions. How do you chain actions? In Haskell, you have this command called do that's used to chain actions. Okay, and how do you use it? So the output type of a do block is the same as the output type of the last action. Do makes the actions take effect in sequential order. Here is the first time you will see any mention of order. Normally in Haskell, execution order is data driven. Okay, what do I mean? If I have f of g of 5 plus 3, 5 plus 3 will be evaluated first because that is what is being provided as a value to g. Right, assume g is some built-in function. G will be executed next because you need the value to be provided to f. Okay, so roughly, okay, we know that lazy evaluation will not follow this strictly when g and f are user defined functions, but roughly when you actually see the moment of execution of f will be the final effect of f will take place after the final effect of g, because g is an argument that is needed for computing something in f. Okay, so f needs a g value to compute something. Okay, so therefore this is fine, but the do block even though there is no logical connection between, so in some sense you can say that there is a data dependency between F and G. G produces some data and F needs that data to undertake its computation. There is a data dependency, and any kind of execution order has to respect the data dependency, otherwise you can do whatever you want, which is why Haskell can freely choose to do lazy evaluation as long as it respects the data dependencies. But when you do, you actually force things to happen in sequence, because when you say print hello then print world, you don't want some arbitrary mix up of these orders. You want the first action to take place and then only the second action, even though technically speaking there is no data dependency or logical dependency between the first action and the second. Okay, so this is the important point. Okay, here is therefore our first non-trivial, let us say input output program. I can print any number of strings I want. I will print hello and then I will say what's your name. So notice that there are two styles. Here you have to indent. Here I am using C style blocks. If you do that, if you follow the second this thing, this indentation is optional. But of course, you would still indent for clarity. Okay, so it also looks aesthetically pleasing. Here the indentation is mandatory. Okay, the indentation is the only thing that tells you what is part of the do block and what is not part of the do block. You can put any number of actions inside a do block, they will all happen one after the other. And now this is very nice because you can have actions, one action whose what that action is depends on the result of a previous action. We will see that. Okay. Okay. And you can have actions that can occur inside a let, where, if then else, etc. These are part of larger actions. Here is a nice Fibonacci function that I have written. Let fibs equals 0 followed by 1 follows. This is a complex Fibonacci function. You don't need to necessarily figure this out. But the point is, I am having a let where I have written something, and then I am saying in and I am saying do something. Let's program this out and let's see what happens. Yeah, I will move to VS Code now. Let me just go back to that same hw.hs and notice one thing. You can write a hw.hs, and I showed how you can actually compile and run this program from the terminal. But as you are writing this program, even though it has a main function and so on, you can still run it inside GHCI for most of your testing, and only at the final phase you compile it as an executable and run it from the terminal. Okay. Okay, now I am here. Let's keep this. And it is not necessary that main is the only IO action. I can define my own IO actions of other names. Let me define a main prime now, or main 1, let's call it. This is a do block, and I am saying let I can write any kind of function here, let, and I can write or let me write an efficient fib while I am at it. Okay, let so it should be first part. So I am writing a function go on n will produce always fib n followed by fib n plus 1. So if I want to produce fib of n, I will first run go on n and then ask for the first component of it. Okay, so go 0 is 0, 1, go n is, let a b equal go n minus 1 in b comma a plus b. Yeah, so that's it. So I start with 0 1 and then repeatedly I shift the right value to the left, and the right new right value is the left value plus right value. I keep on doing this. This is exactly the same as the Fibonacci, this thing that we are working with. Okay, so I have a let here. I have defined my let in do I should always use parenthesis here because I want to right now say the 100th Fibonacci number is, and then I want to write a number. For that I need to use plus plus. Okay, so I'll use dollar. Remember that dollar is used to treat the whatever follows as one whole complex expression, as one complex expression which is an argument to put string line. Okay, so now I'll just write a string here, the 100th Pingala number, let's call it, to give it its real name. At this point I should say plus plus, but I can't say fib n because fib is a number and I can't do a plus plus of a number to a string, so I should say show fib 100. Okay, that's it. So that's my do block. Let's see if this compiles. Let's get to this GHCI. Let's try to load hello world.hs. Yes, it compiles. Very good. So now I can say main one. Main I can say it will just print hello world. Let me clear the screen. Main one. Yeah, so it says the 100 Pingala number is this. Ideally, what you would like to do is you would like to ask the user, give me a number, I will give you the nth Pingala number. Okay, that is what you would like to do. Let's, in a few slides, we will see how exactly to do that. But I hope it's clear how to do this. Let's write a couple more examples. This is an example where I used let in and then wrote a do action. Chained action using do. I could also do something else. I could also say something like this could be a much simpler function. Do act 1. While I am at it, I could also use this style. Act 1 followed by act 2, and here I am giving semicolon where act 1 is just put string hello and act 2 is just put string line world. Okay, so you could have this also. Something is wrong. No, nothing is wrong. Okay, and now we can try to just see if this executes. Let me reload this function. Okay, so I am able to print hello world. Okay, so I can say do and then I can have a where there, or I can say let something 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 in do. Okay, and even inside specific actions of a do, when you're chaining multiple actions, you can have let there also. We'll see examples of all that later. Okay, here are more actions, not just put string and put string line. Print is an action, and print is a little more versatile than put string line. Put string and put string line will only show strings on the screen, whereas print will take any value of a showable type and put it in the string, put it on the screen. Essentially, print is composing show with put string line. Okay, so that's the point. Output a value of any printable type to the standard output with the screen and add a new line. So print is nothing but is nothing but put string line and show composed. Okay. Okay. So there is a put char which will put only one character on the screen. So that's also, but all these are IO unit, right? Because they do not produce any result value of any merit of any usable nature, but they have a side effect, and the side effect is that of printing something to the screen. So that is why you tag them with IO, but the result is not useless. We will soon see something where the result is actually, the result produced by the action is a useful thing. Okay. So put char only prints one character on the screen. Get line, this is our first thing where you have a IO action whose result type is a meaningful type. Okay. IO string, what it will do, it will actually read from your standard input, which is typically what a user enters on the keyboard, and it will return it as a string. Okay. So this is important. Get line, the side effect of get line is the consumption of a line of input. Put string, at least you can imagine, you can conceive what the side effect is, which is that earlier my screen was blank, now it has one line on it. What about get line? Get line is also similar, because remember that among the things that are part of the state of the real world are various input output buffers. There is something called input buffer, which connects your keyboard to your main processing unit, in which is stored all the keystrokes that the user has entered, and that buffer will be, one will keep on filling that buffer till at some triggered by whatever, the buffer will be processed and processed by the processor, let us say. So get line will force the processor to process one line. Earlier the buffer had one extra line, now that line has been consumed. Okay, that is the state of the that is the change of the state of the real world. So the return value is a string, because when you ask the user to enter something, the user enters something, that is something of value that needs to be used by the program. Okay, that is a legitimate value that is used by the program, and it's not dummy, and that is why you have a non-dummy return type here, string. Okay, there is a side effect, there is also a value that is produced. The value that is produced is whatever the user entered. Okay. So you have similarly get character, which put character writes one character to the screen, put string writes one string to the screen, get line gets one whole line, get character gets one character. Okay, it reads the next character from the standard input. Okay. So okay, so now, but you have get line, which is of type IO string. It is, you ask a user to enter a string, the user enters a string. Okay, but the string needs to be used by the program. How will you extract that value? Okay, so binding is about extracting the value. How do you okay, and notice that getLine does not have any arguments, because you say getLine and getLine is supposed to, there is no argument that is useful here. You're just saying read the next line of input from that the user enters, so you will have to just go and read the next line of input. There is no argument, there is only user input, there is no argument. Sometimes I would have confusedly used the term input instead of argument. It was clear in those circumstances, but now that we have used input output also, then I will try to, as far as possible, maintain this distinction and say that argument for something like x that you supply to f when you write an expression of the form f of 5, f of 10 or whatever, that's an argument, whereas getLine reads a user input. Okay, so there is no argument for getLine. Only user input. Okay, so this is something that you have to remember. So is there a way to use the return value, the value that has been, how do you extract this value? To extract this value, you need to actually say that, oh, this value should be given a name. Essentially, bind means give the value. There should be a way to name this value and refer to it later by name. And that is what is called binding. This whole process is called binding. Okay. And the syntax is simple. The syntax is just this. But once again, so there are sometimes, so do not this is for people who have been used to other imperative languages or things like Python and so on, where you have a way of assigning values to variables and changing the values assigned to variables. Okay, that is the notion of mutation, etc. That is not what we are doing here. This left arrow and this equal to, all it is doing is just this is just associating a name. We are only associating a name to an expression or value. No mutation allowed, as it at least. In this course, most probably you won't see any mutation. Okay, good. So let's now come back to this. So how do you use this? You can say, please type your name, and the user types the name, and the user, hopefully the user listens to the program and types a name. And the way to read the whatever the user has typed is to use getLine. But the getLine has some return value, has some actual, it has produced a value which is the whatever string the user entered. We will use n to refer to that string, and the syntax for that is to say n left arrow getLine. Okay, that left arrow, this is a special font that I am using, which is writing it as a left arrow. In the keyboard, you will have to say less than followed by arrow. Okay, less than followed by hyphen. Okay, good. So I am saying refer to the result produced by this getLine as n, and later I can use this. I can say hello, and then I can say plus plus n. Okay, that's, I am addressing whoever that whatever that name is and saying hello to that person. Okay. Notice that you cannot say put string line hello plus plus getLine, because put string line expects a, put string line is of type string arrow IO unit, whereas this getLine is not even a string. Though this hello plus plus, since this is a string, it expects this to be string. This is not even a string, not a string. Okay, rather it is a IO string. You cannot add a, you cannot do plus plus on a string and an IO string. Okay, so that is why you have to first associate a name to the return value of a IO action. And since getLine is of type IO string, when you extract the value, n will be of type string. Now this is fine. Okay, you can do this. Yeah, getLine is not an act, is not a string, it is an action that has a return value of type string. Okay, good. So the return value has to be extracted and bound to a name. before being used. Okay, good. So the next thing that we need to do is to see how you can repetitively perform some actions, which is a common feature in all programming languages. But before that, I will go to the VS Code and show you how to do input followed by output. We go to the same hw.hs program and we add instead of main, we can actually change it, and no, I'll have a main 3, let's say. Right, at this point you are asking the user to enter their name, and the next action that you do is to say getLine. See, here I am using less than followed by hyphen. Okay, that is this thing, and getLine is the next action, and you are binding the value produced by getLine in n, and now you can use the value and you can use the name n now. Yeah, n is just a name that is associated to that value. Okay, I am saying hello n, and now this is a little more interactive and this is a little more this is a slightly more convincing input output program than whatever we have said, we have seen earlier, because earlier we just printed out something, okay, rather than actual interaction. Okay, so now let us go to GHCI, let's reload this program and let's main 3, let's say, yeah, please enter your name. It's saying I'll say Suresh. Yes, it's a hello Suresh, right? So the output depends on whatever it is printing out, depends on whatever input I produced. Okay, this is true interaction. Okay, and it is not just some pre-decided thing that it is printing. It is printing something based on my input at the terminal. Okay, let me move back to the slides. Right, I want to read a line and print it out 10 times. Let us say this is a very minimal kind of repetition that I want to do. Right, I can do this. I'll say input, I'll do getLine, I'll bind the value to this name called inp input, and I'll say print often. Okay, this is just some function that I have. Sorry. I'll have print often, which is a function 10 times the input. Okay. So print often 1 times is just saying put string line str. Print often n times just means do put string line str followed by print often n minus 1 str. See, you can have recursive actions, recursive calls. Okay, recursive calls are permitted inside a do block, and this is one of the most this is one of the simplest or most fundamental ways of repetition. We will see other ways of doing this, okay, in a bit, but this is one of the most fundamental ways of repetitively performing some IO. Let's program this. Okay, I'll go to hw.hs again. Okay, I'll have a main 4. We have so far not given any types to anything. All these things are of type IO. Print often will be of type int arrow, string arrow, IO unit. Okay, so we are just making this recursive call. Let's just try to see if this works. Let's see if this works. Let's get back to GHCI. I'll reload the program. I'll say main4. Okay, now it says please enter a string. I'll say Haskell IO is cool. Okay, and then suddenly it starts printing it 10 times Haskell IO is cool, and therefore becomes non-cool. But that's only my doing. Let's get back to the slides. Okay, so this just tells you how you can repetitively perform simply by having recursive calls inside a do block. Let's get back here. Right, so there is something mildly not satisfactory about this, which is that I started the recursion with 1 rather than 0, right? So suppose I want to do print often 0 string, okay, how do I do it? Print often 0 string is supposed to be no action at all, right? I am not supposed to do anything. Print often 1 string means I put string line once string, right? Print often n times string means I do put string line once and then print often n minus 1 times. That is fine. What if that n is 0? Okay, so now there is no meaningful way to say this, right? You can't just define it to be unit, because unit is of type unit, not IO unit. So there needs to be some way to, then you need a yeah. So this unit is of type unit. We need something of type IO unit. Okay. So essentially you need a way to promote the value unit to an object of type, to a value of type IO unit, and the way to do that is called return. Okay, return is a function. Return is actually a very general function, but for our purposes, return is a function of type A arrow IOA. Okay. So if V is a value of type A, return V is of type IOA. You should not confuse this return with languages like C, Java, etc. Their return means return program control to the caller. Along with this return value, let's say. Every function will have a return, may have a return value, and the return value is returned to the caller, along with the control also being returned to the caller. Okay, there is a notion of control, etc., etc. In Haskell, so far we don't have any notion of control, whatever. It's all rewriting. Even this chaining of actions inside a do block can all be related to functions and rewriting and behavior of various functions. Okay, so this return is perhaps an unfortunate choice of words here. If you sometimes the word pure is also used. Pure is also of type A arrow IOA. Okay, or it's even more general. It's A arrow MA, where M is a monad. These are concepts which, if we have time, we will talk about at the end of the course. But for now, pure is a function and return is just a version of pure for IO. Okay. Maybe return itself is general. We can check in GHCI. Okay, in imperative languages, return is used to return control to the caller. In Haskell, return is just a wrapper around a value. Okay, you have a value unit of type unit. Return unit will have type IO unit. Okay, that's all. Okay, you just want to promote the type of a value without affecting anything else. So, for instance, if you do a return E, what you are doing is you have a E of type A, you are promoting it to type IOA, let us say, and you extract the value of that expression which is of type IOA and bind the value to X. So, X is now a value of type A and it is nothing but E, okay, the value of E. And then if you perform some other action later where you refer to X, this is the same as saying let X equal to E in act, okay. Just to tell you what the behavior of return is. Return is doing nothing but wrapping the wrapping a pure value inside some IO action, okay. Return, if you will, is sort of the, or if you will, binding is the inverse of return, okay. That's exactly what this is illustrating, this particular thing. Okay, so returning to this, so here is a much better way of doing your read a line and print it out 10 times. You say print off on 10 the input, but rather than having the base case be print off on 1 string, I'll say print off on 0 string, and here I'm just saying return unit. What this means is do not do anything. Okay, just produce the but for purposes of type compatibility, promote the to a value of okay, that is what is happening here. Okay, promote the value unit to a value of type IO unit. That's all that this return is doing. There is no return of control or whatever, though sometimes it might appear that that is the last line in a recursive action, so it looks like you might be returning some value to the caller, but that's not what is happening here. Okay, there is no explicit return of value to a caller or whatever. A function calls everything is expression, you see, because if I have f applied on or f with supplied an argument g of something something, g whatever that value is evaluated and then f is evaluated on that. There is only such kind of there is only this kind of evaluating of function values. There is no need to explicitly return control or whatever using some keyword like return. Okay, so the return here is just this doing the value of this promotion. Okay, good. And now print of an n is just the same as usual. Let's just go back and modify our earlier program with this and see if it works. Okay, so here we have this hw.hs. Here instead of having this thing, I will say okay, and if you are uncomfortable with return, I could always use pure. That should also work here. Okay, let's check in GHCI. Okay, let's go to GHCI. Let's reload our function. Let's call main 5, main 4, right? It works. It is compiled already. So yeah, same thing is happening. So let's check for the type of return. Right? Return itself is general. It's just saying IO is an example of what is called a monad, which, as I said, we might look at it for a lecture or two later. For now, whenever you see monad, think of it as IO. Okay, so return is of type A arrow IOA. Okay, similarly pure, which has the same type. Okay, pure has a more general type. So these are all concepts which we might look at later. Okay, or maybe not, but in a second course in Haskell you can learn all this. Okay, but the point, okay, for now we will just stick to return, or why not, you can just use pure always. Okay, because any monad is an applicative, so pure should work. In case, so you can strictly always work with pure so as to avoid confusing yourself with the keyword return here. Okay, so return is just a function in Haskell which promotes types. Pure is also doing the same thing. So you can either use pure or return. Okay, fine, good. So this works. Let's return to the slides. Here is another example of repetition. So get line itself can be implemented in terms of get char by doing repetitively. Get line is nothing but get one character, call it C. Okay, if C is the new line, then you just return the empty string. Okay, return, yeah, this is of type string. So this whole thing is of type IO string. You are not returning any value like in an imperative language. All you are just saying is that, okay, the value produced by getLine on is just the empty string. Okay, in case somebody pressed the new line at the very beginning itself. Otherwise, you recursively call getLine and then you finally return C followed by C's. Recursively calling getLine will read the remaining characters. Then finally, you should put the character you first read. This was the character you first read. That should be put in front of all the C's. Okay, and you are just promoting this to an IO value. Once again, there is no return as in returning in an imperative language. I can do the same thing using pure, or maybe you can do it on your own as an exercise. Okay, just to get more familiar with this. I'll just look at one more example before I end these slides, this lecture. Right. So I can actually do some action in time. So here is an example where I am saying I can provide an IO action as an argument. This is nice. So this get line is just a particular example of this. I am just saying not get line, the earlier print often or whatever was a particular example of this, because here I am saying do a particular action A n times, no matter what that A is. Okay, so doing A 0 times is return empty return unit. Doing A n times is nothing but A followed by n times n minus 1 A, and now I can, the print often string was nothing but get an input and put string line n times do this whole thing. Oh, this is a new thing. N times I am reading n different inputs and printing all those inputs as, on the screen. So let me just program this and show it for you, and I will stop this lecture. I'll call this main 5. I can use also a dollar here instead of that. So int is the first argument, an IO action is the second argument, and what is produced finally is an IO action, and n times 0 of any action A is nothing but return unit. This is a, think of it as a dummy IO action. N times NA is nothing but do A followed by n times n minus 1. Okay, I have this, and maybe here I should add a prompt, okay, and that's basically it. So let's try to see this, how this works. Okay, so GHCI, I am reloading this function, this program. Let me clear the screen, and now I'll say main 5. Please enter a string as it says. See, whatever we are entering is being printed out. So this is really interactive, right? Okay, so now we are done. Okay, so thank you. I shall stop this lecture with this. So we've seen the rudiments of IO in this class. In this lecture, we've seen basic IO actions. How are IO actions different from functions? Okay, how to run our own standalone GHC Haskell program by compiling. Of course, we haven't really written any highly non-trivial program that needs to be compiled and run on the terminal, but it's okay. We are able to test all these different IO based functions from GHCI itself. Okay, and importantly, we looked at several basic ways of doing repetition. The one way we have seen now is the most fundamental, which is to use recursive function calls inside do blocks. Okay, I shall stop with that. Thank you. We will meet in the next lecture.